Okay, so we're going to talk about graphs again today, along with some kind of spectral properties at the same time. Uh, well, let me quickly recap what we're doing. We're kind of in this linear algebra block, which is a little bit heavier. Like they're kind of building on top of each other, maybe a little more than the stuff from earlier in the class. But it started with we're really analyzing random walks, which of course is a very standard topic in the randomized course. It started with the existence of just a stationary distribution and also kind of getting used to random walks. Um, it went to kind of talking about things like hitting times and cover times, as well as introducing objects like the Laplacian. That's going to be kind of the primary character today. Last time we talked about a more refined bound for analyzing random walks, right? So we had already established that there always exists a stationary distribution. But then the question became, how fast do you converge to a stationary distribution? And we sort of got this exponential rate of convergence that's governed by that gap between that maximum eigenvalue of 1 and sort of the absolute values of the other eigenvalues. Okay. So suddenly you could start saying something much more kind of quantitative. And oh, I guess here then is that theorem. Right, 1 minus gamma to the k, you can think of e to the minus gamma to the k. But gamma is sort of the difference in absolute value between that first eigenvalue of 1 and any of the other eigenvalues, which will always be attained by either the second eigenvalue or the most negative eigenvalue. Okay. Okay, so that's what we showed last time. Um, Now, of course, you look at this and you look at a graph, you're like, what does mu2 of a graph mean, right? At some level, it's sort of an algebraic property. It's a little bit abstract. So we're gonna connect that a little bit today. So, okay, so today we're gonna talk about a couple things, something called conductance, something called Cheeger's inequality, and then kind of replacing that convergence bound with something based on conductance. And conductance is going to be like a graph property. Okay, there's no linear algebra kind of explicitly involved. So the goal is to sort of take this kind of thing as a function of these mysterious eigenvalues and basically replace gamma with some kind of fixed property of a graph. Okay. So okay. So conductance is very close to related to sparsity. We talked about sparsus cut at least once. But sparsus cut, the idea was something like you know instead of just worrying about cuts that remove small number of edges and disconnect it, because then you just might be removing leaves. That's not so interesting. You're kind of looking at the ratio of like how many different pairs are being disconnected. Okay. So we looked at this ratio of the edges cut versus kind of the number of vertices on each side. But the denominator, kind of biases more evenly divided sets, right? Because it's always going to be maximized when at kind of n over 2. Okay. So this can be much more useful if you want to do like some kind of divide and conquer, where you really want to split the graph roughly in half. If you're just trimming off leaves, you're not going to get a good divide and conquer kind of recursion. Okay. So okay, so right, we did some algorithms for sparsus cut before. All right, so conductance is going to be a similar kind of ratio. But the denominator is going to change a little bit. So let me just quickly go over some notation. Everything will be in an undirected graph. I'll use W for edge weights. I guess I've always been using that. I use that delta S for like the cut induced by a set of vertices S. Okay, so I have S, and that's delta S, boundary or something. That means if I put W around that, it's like the weight of a cut. And then volume is going to refer to kind of weighted degree. The volume of a set of vertices is for every vertex, I'm going to sum up the weighted degree, sum up the weighted degree, sum up the weighted degree. Okay, so there's a total number of edges incident to S, double counting the edges that are inside. Okay. All right, so so conductance is going to be a lot like sparsity, except we're going to replace the size of S, the number of vertices, with the volume. Okay. So first of all, this is morally very similar to if I have done the product of the two. Uh, okay. Because at some level, if you know that one side is, you know the bigger side is always at least the total volume over 2 anyway, right? So you already know the bigger side up to a factor of 2. So the distinction between the product and the min is not very significant. But okay, so what is this saying? I want to look at all the vertices S, and now when I'm cutting, looking at a cut, I'm looking at how many edges I have to remove, and let's say this represents the smaller side. Relative to the volume inside. Okay. Yeah.
Is that bias associated like approximates?
Is that work?
Like for S is a subset of E for S.
Oh. Yeah. Yeah. Okay. Okay, so just a different notion, but we're going to see that it's sort of more convenient to some Laplacian stuff. It still can be actually. One sec. Before going into it, I have some interactive examples for us. Okay, so I have 3 graphs here. Okay, and then we're going to look at the sparsity of each graph, where that sparsity is really defined by the most sparse cut and the conductance of each graph, right? So the only difference is the denominator. And this is not like, super well defined, but you basically have 3 choices for each one, sort of like high sparsity, low sparsity, medium sparsity. What do they mean? I don't know. Same with all of these. Okay. All right. So that's 6 different things you can vote for. First of all, who's not voting? Okay, 4. One of the not voters are a little bit too enthusiastic about them. Okay. So now, okay, we can do the sparsity row first, and we'll just do one graph at a time and kind of say, okay, is it high, medium, or low? Okay. Okay, so let's take this first graph, which is 2 clicks connected by a couple edges. Uh, you have a choice between kind of high, medium, or low. Who would say this has high sparsity? Or yeah, quantity, which means not very sparse, I guess. Okay, 0 for high. Anyone for medium? Okay, four for medium. And then what about low? Okay, one liar. Okay, so most of you thought it was pretty low. All right, what about the second graph? The second graph, I have a complete graph. I replaced one of those complete graphs with just a cycle, right? A minimally connected thing. Uh, who thinks that this will have maybe a high sparsity thingy now? High sparseness. Okay, 0. Who still thinks medium? 1, 2, 3, 4. For medium. And then what about low? 1, 2, 3, 4. Okay. Okay, people are dropping off. All right, and then lastly, what about this complete graph? Just all things are connected. Who thinks this will kind of be high? Okay, most of you. And what about more like medium? And what about low? Okay. All right. Good. Before moving on to conductance, okay, so most of you thought it was low sparsity. What would be like a very sparse cut? Just right down the middle, right? Because you have half the vertices on each side. All right, what about the second graph? What would be a very sparse cut? The same thing. And what would be the sparsity? It would be the same. So what happened to those of you who changed your mind? Maybe no one actually did. Maybe just 3 people fell asleep. Anyway, sparsity doesn't actually change because we're not really counting the volume. We're just counting the number of vertices on each side. That's the only point I wanted to make. And then, yeah, so a complete graph is the kind of the most connected thing. All right, so yeah, it's pretty high. All right. Okay, now let's do conductance. Okay. All right. Who thinks that that first graph has very high conductance? Okay, 0 high. What about medium? Okay, 0 medium. How about low? Okay, very good. All right, now let's look at this next graph. Who thinks that this has pretty high conductance? Okay, still pretty not high conductance. How about medium? All right, now we're starting to get a few more. Maybe 2n/3. And then what about low? Okay. All right, and then what about for that last graph? Who thinks that it's pretty high? What about medium and low? Okay. So, okay, everyone thought that this was low this time. Nobody even thought this was medium. I guess here now you even have very high volume on each side too, because you have all those connections in between. Now this time though, less people or more people went for medium. What was the thinking? This side's volume is actually not super high anymore. It's not even clear to me what the kind of lowest conductance cut is. It might still be the same cut. Um, and then for this, it was about half and half, but it's still about as high a conductance as you're going to get. Okay. All right, because conductance is actually always between 0 and 1 anyway. This is going to get pretty close to 1. Okay, good. So that is or some constant. Okay. All right, but at least we get some sense of these values. Okay. Let me give you yet another definition of our good friend yeah.
What'd you say the drop to meter? Denominator? Oh, that.
Yeah, so you can look at things like the product or the minimum of the two. Okay? But let's say that volume of S is let's say S is the smaller one. Okay? Then you know that this thing is at least N over 2. Or sorry, the total volume over 2. I'll write big V for total volume. And you know it's at most the total volume. Okay? So you basically know what the bigger value is up to a constant factor. So if you try to optimize this, you're going to get something similar to optimizing this because the volume of the bigger set is only going to affect things by a constant factor. That's all. Okay. We're going to be, sparsest cut, the best approximation we have is like log n, or you can do slightly better, but so we're far from a constant. Okay. So I'm going to give you yet another definition of the graph Laplacian. If okay, so just to recall, it's this kind of symmetric matrix. One way to define it is like this: you put in any vertex potential, and it's always going to look at the endpoints and take the difference squared. Okay. Now, all right, something like this. All right, so let's say I'm looking at Laplacian of just like a single edge. Okay. Well, what do the entries of this Laplacian look like?
U is 0.
U is 0. Well, no, actually. Uh, any other guess?
Is the phone one something?
Is it all ones? Not quite either.
One's on the day.
It's going to be ones on a diagonal and negative ones off the diagonal. Okay, if you kind of work through. At least it's easy to verify in hindsight. I mean, it's harder to guess, but it's easier to verify. And so if I for example let capital B be the diagonal matrix, the degrees along the diagonal, and I let A be the it's an undirected graph, so symmetric adjacency matrix. Okay, then you can also write L as D minus A. Okay, you can kind of see that here, right? This is just one unweighted edge. Here's the degree on the diagonal, -1 for the adjacency matrix. If you get a weighted combination, you just get a weighted combination of degrees minus adjacency matrix. Right? Okay, good. All right, so that's going to be a helpful identity today. Let's see what happens. Okay, so why are we looking at conductance and not something like sparsity? It's because it's going to be easier for us to relate to the graph Laplacian. Okay, so all right, so let's just start here. Uh, so if we remember that, yeah, okay. So if I expand out, this top numerator here. Okay, so let's say I want to basically I'm trying to come up with a nice relaxation, a continuous relaxation of conductance, right? So let's look at the conductance of a set. That's going to be the weight of the cut divided by the volume of the set, assuming that this is a small set. It's less than half the volume of the graph. Okay. Now, if we look at this quantity here, this is going to be summing up over all the edges that are cut by S. Well, it's really going to be summing up, yeah, the weight of E, uh, and it's going to kind of look like 1 minus 0 squared. Okay. So if we go to the usual definition of a Laplacian here, you're normally going to look at every edge and take the difference of the endpoints. Okay. But if I plug in something like the indicator vector for S, that just means it's a 1 for every vertex in S and 0 elsewhere, right? That means if I have an edge where both endpoints are in S, I have 1 minus 1 squared, that's 0. Or if I have an edge with both endpoints not in S, I'll have 0 minus 0 squared. But if I have 1 in S and not in S, in other words, it's cut by S, then I'll get 1 minus 0 squared. Okay. So the numerator, because it captures cuts, right? That agrees. And if we look at the denominator, that's just a diagonal matrix of degrees, right? So we're just summing up the degrees in S. Okay. So what's nice is that well, it's some kind of relaxation, right? Now I can relax this to kind of any vector. Okay. Now what we're going to do is define a normalized Laplacian. This actually kind of came up slightly in the theory seminar earlier today if you attended it. Okay. I'm just going to take L. I'm going to divide both sides by square root of D. Okay. Why is that useful? It's mostly kind of technically convenient. So let me explain. If okay, so this is like okay, this semantically makes sense for us, right? This models conductance directly. But from a linear algebra point of view, this expression is a little bit more comfortable. Why? Does this look familiar? I should note that M is a symmetric matrix still, because L is symmetric and we're just applying D to the minus 1/2. Why is that the second expression maybe? Uh, yeah, so this is closely related to how we got eigenvectors last time. So last time I said something like, oh, the top eigenvectors, I maximize y and y subject to y being unit vector. Equivalently, I could have said just maximize this ratio, and this denominator means that basically only thing that matters is direction. This is a scale invariant ratio. Okay, so here's something kind of semantically meaningful, and here's something that starts looking like eigenvectors of M, which you can compute and you can interpret based on eigenvalues and things like this, right? So this is sort of what we're looking for from a kind of graph algorithms perspective. This is what we're looking for from a let's make the most of linear algebra perspective. But if I want to make this connection, what would the value of y become? Square root of d times x. Okay. So if you just kind of plug this in down here, then you're going to get this. Okay. But now what's very nice is that if I want to kind of say find x that minimizes this as some kind of relaxation for conductance, uh, then it comes close to, oh, do some kind of eigenvector computation for m, which we can do. All right, so good. All right, so now So much jargon. But anyway, if you remember this, normalized random walk analysis we did, I guess just Tuesday, so long ago. We did all these nice things like, once you make the randomized walk symmetric with this kind of similarity transform, you can diagonalize things and you still have the same eigenvalues, which means the first one is 1 and all this stuff, right? And then we're able to analyze this because we know how to take powers of Q very easily. And that kind of led to this bound. Now, okay, now what I want to do is I want to relate this normalized Laplacian. Okay, right now we're kind of still making connections. I want to relate the normalized Laplacian with this random walk matrix. Okay. So for starters, this is just a plugging in the definition. Okay. And if we expand out this yet another definition of the Laplacian, I plug in d minus a like that. Now I get this. Okay. Now what might I do to simplify this? Okay, so we'll distribute what happens to the d. So okay, this first term will turn into I, since you have these kind of inverse square roots. And what about d minus 1? Huh? You get q. Okay, so you get this. All right. Okay, so this normalized Laplacian is the identity minus the normalized random walk matrix, which we worked so hard to understand last class. All right, so what does this say about M? Yeah, it does say M is symmetric, but we already knew that from the initial definition. Uh, okay, well, let's see what this is. Oh, okay, well, whatever, that's also fine. It's also related to I minus R, right? All right, okay, how about this? Now that this is there, what does this say about M? Well, for example, it says that M is blank to I minus R. Similar, right? And that starts to tell us that M has the same eigenvalues as I minus R, which we understand also well, right? Now, okay, now M is not the same eigenvalues as R. That would be very straightforward. It's I minus R. But I is not so hard to understand, right? It's just the identity matrix. So like, what are the eigenvalues of I minus R related to R? 1 minus the eigenvalues of R, right? So that means an eigenvalue for M becomes what is an eigenvalue for R, but it's not lambda doesn't become the eigenvalue for R. Instead, 1 minus lambda. And then an eigenvalue, or lambda minus 1. Hopefully that's correct. An eigenvalue lambda for M becomes which eigenvalue for R becomes what eigenvalue for M? I don't think is it 1 minus lambda? All right, someone can double check. Hopefully you got that right. Okay. Uh, so should this be 1 minus lambda? Yeah. R is equal, sorry, R is similar to I minus M. Okay. I think this is actually 1 minus lambda. Don't worry about the number of squiggles. The other one's 1 minus lambda. If something is an eigenvalue, Jesus. Something like this, right? Oh, did I get backwards again? Oh, are they both lambda minus 1? No, no. Oh, it was okay. Life's okay? All right. Okay. Doesn't matter. It's verifiable. Okay. All right. So this is what we're going to try to prove today. And this is what's kind of interesting. Okay. Let lambda 2 be the second eigenvalue of M. Okay. Now, conductance of a graph is actually something we're interested in. That's a natural graph property, right? We want to use that for things like divide and conquer. It says that the conductance of the graph is between lambda 2 over 2 and square root 2 times lambda 2. Okay, where lambda 2 is the second smallest eigenvalue of the normalized Laplacian. Okay. All right. So, right. Okay, so this is very interesting, right? Because it's connecting, a natural kind of combinatorial property with an analytical property or algebraic property, depending on how you see eigenvalues. Okay. And at some level, like, low conductance cuts are hard to get a hold of, right? So the fact that the eigenvalue is actually playing a role is kind of surprising. Okay. Now, the obvious kind of very unusual thing. Oh, did I have something more written down here? Oh, okay. Smallest eigenvalue is was 0. Okay. Uh, so okay, so the eigenvalues of M are between 0 and 1, just as the 1 minus the R ones. And now one thing kind of unusual is, of course, the square root, right? That's not a typical approximation. Now, we should mention that if lambda 2 is very close to 1, it's at least some constant, then the square root's not that big a deal. And you actually get a constant factor approximation for conductance if lambda 2 is a constant. Okay. So if lambda 2 is at least, 0.5 or 0.1, right, then taking a square root, you're not losing that much compared to lambda 2. So you'll get less than equal to something something lambda 2. Okay. But why is that actually important? It's because uh, so that means when the conductance of the graph is very high, above some constant, we can actually verify that it is above a constant. Okay, so it's not a normal approximation ratio where we always get a constant for all values of conductance, but when the conductance is starting to approach 1, it's above some constant, you do get a constant factor approximation. In particular, graphs with high conductance are something called expanders, which is going to play a big role next week. Okay, so although we don't have a constant factor approximation for conductance in general, you can actually verify that something's an expander this way. Okay, so that's very important. Now, the square root stuff, especially when things aren't constant, do give a lot of headache. It's not very wieldy. You do the math, it gets very messy when you start trying to use it in situations, and it leads to things like the small set expansion hypothesis and things like this, which are at some level almost asking if this is tight, but it's a little deeper than that. Okay, but there's sort of a lot of just in case you get exposed to that terminology, reading some papers, there's a lot of kind of fallout from this awkward square root lambda 2 that I wanted to mention. Okay, good. So we will prove that, but first let me try to connect things together. So what do we know? So we have some convergence rate for stationary walks, depending on eigenvalues of the random walk matrix, right? And we have some mapping between eigenvalues of the normalized Laplacian and eigenvalues of the random walk matrix. And then we have this Cheeger's inequality that relates to eigenvalues of the second smallest eigenvalue of the normalized Laplacian to this conductance parameter. So once you start putting that all together, right, we might be able to start bounding the mixing time, the convergence rate, in terms of the conductance of the graph, and sort of remove the eigenvalue from is just a middleman, right? And the conductance of a graph sort of actually is a little bit easier to interpret. So yeah, so at some level, a graph with very high conductance, I'm just looking for some white space. So if a graph had very low conductance, you should think of like a, very dense set with very small number of edges leaving it, right? That would be a very low conductance cut. And if you imagine doing kind of like a random walk, every time you're about to maybe leave, you have all this kind of volume on the inside pulling you away, right? Like we know that a random walk, the stationary distribution is proportional to the degree, right? So it's going to be in this side of the graph with something proportional to the volume, right? So a low conductance cut kind of represents these bottlenecks from a random walk point of view, right? It's really hard to get out of this set because all these edges kind of pulling it in, all this volume pulling it in, and very few going across. Okay, so intuitively, it would make sense that a low conductance graph would have a low mixing time. And then I guess, we haven't demonstrated any converse, but maybe you're hoping that then a high conductance graph, at least it wouldn't have this kind of bottleneck. And so you might help it mixes it well in general. Okay, and so that's what we're going to actually show, which is a pretty strong statement. So we'll get to it. Right. Okay, so eventually we're going to show something that looks like this. The convergence is going to be e to the negative, something to do with the conductance of the graph. Okay, so instead of converging based on the eigenvalues, it's going to converge based on the conductance. Okay, but it's really just connecting those three things together. Okay, so all right, so we're going to do it in two steps. So one is okay, so remember gamma is either the second eigenvalue or the nth eigenvalue, the negative. So let's first assume that it's the second one. Okay, so I'm going to assume that mu2 kind of determines the gap. Okay, so that you have something like this. Okay, and so if we just kind of plug in our theorem, something like this, right? And then, okay, and now that'll become like mu2, right? Now, how does, okay, so you have mu2, but eventually you want to get to here. Okay, so what is mu2 equal to in terms of trying to kind of get closer to conductance? Oh no. Okay, so I'm up to 1 minus lambda 2. Okay, so 1 minus gamma is going to become 1 minus lambda 2. This is to the t, or t steps, right? And you get, we do our usual e to the negative t lambda 2. Okay, and now what? Yeah, now we plug in, ultimately we're going to plug in this side, the log where you have to square both sides and divide out the 2. And you'll get something, why? You get something like that. Okay, so it's really just plugging in and connecting, yeah. Well, my handwriting is not very good. That's very polite of you, but is it okay now? Yeah, I didn't want to write out the delta max, delta min. Yeah. Okay. All right, so anyway, we're just connecting the two and you get some bound terms of conductance. The only thing though is that we made this convenient assumption about mu2 being greater than or equal to, right? Which may not be the case. For a bipartite graph, mu n is equal to -1. Okay. Good. So, okay, so the random walk actually may not converge well if mu n is equal to -1 and something like this. Can anyone think of some trick, some kind of related random walk that might do better? You could think of like a bipartite graph as a bad case. And suppose you wanted to do a random walk on a bipartite graph and converge to a stationary distribution. You're allowed to change the random walk though. I mean, in this game, okay? It'll be a natural adjustment. Well, I don't. Yeah. Well, you cut the bipartite graph, then you just have two independent. No, no. Okay. Wait, let me see. Okay. Okay. So that's okay. Here's a different question, maybe. Okay. So the issue is, okay, how can I try to force mu n to be kind of far away from -1? I really want to be governed by mu two. Mu two is the thing I can relate to lambda two. Now I'm kind of trying to think of a hack that could help. I'm not sure if I mean, I'm trying to see if I can make it guessable. Um, mu n, that's the smallest eigenvalue. So the
between 0
0 -1. No, 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 they're between 1 and -1. So Frobenius says that all the other eigenvalues will be bounded in absolute value by 1. Yeah.
loops, I can stay in the same place.
Yeah, okay, so we're gonna add self loops. Another way is to think of something like a lazy random walk. And you can think of how this might help on a bipartite graph. Okay. So half the time you'll do the random walk as usual. You just follow an edge. The other half of the time, we're just going to stay there. So you're just going to flip a coin. You can think of that as like, if you have degree 10, I'm going to add 10 self loops. You find that helpful. Okay. But you're just going to stay at the same vertex half the time. And so that'll help immediately for like the bipartite graph case, right? Now you're like really could be on either side at any moment of time. Okay. Now, what does the random walk matrix uh, look like, relative to R, right? R is the regular random walk matrix. Maybe S will be the one for lazy random walk. Yeah. Yeah, so those staying can be modeled by I. Okay. So half the time you just stay put, that's modeled by the identity matrix, and half the time you'd actually take a walk. And why is that nice from our perspective of, kind of massaging the eigenvalues? Yeah.
That's 0 because the smallest one -1, which is just this. Oh, 1 that is so.
Yeah, actually, that's actually, oh, that's better than what I have coming up. Okay, so the smallest eigenvalue of R is -1. So this is at least -1/2. And you get +1/2 always. So all the eigenvalues are immediately non-negative. What was I thinking? Okay. Anyway. Okay, so that makes this okay, so okay, we'll just erase it. It's easier to erase than to write, so luckily that's okay. All right, so what we're going to do is we're going to actually not show that the random walk itself converges based on the conductance in general, but that the lazy random walk will converge fast. Right? And obviously it's not so hard to code a lazy random walk if you can code a random walk. Okay, so the real question is just what is gamma and working through it. And again, I'm doing something way too clumsy. Uh, good. So this, as we as was pointed out, we just know that the max is always going to be attained by this thing, right? Uh, good. So oh, that's okay, okay. Maybe that gets us to this point. Okay. All right. So that observation gets us to this point. Maybe we can leave the whatever. Okay, but since all the eigenvalues are uh, non-negative, it's still going to be attained by mu2. Yeah, I don't know why. Okay, so I worked a little bit too hard, or drank a little too much coffee, or didn't sleep enough, or they're all equivalent. Uh, in any case, mu2 is going to come up. Does that mean I'm giving up an extra factor of 2? Maybe. Okay, so you get something like 1 minus mu2 over 2. Again, I think you can just drop this. Kyle's observation is better. And here, 1 minus mu2 is lambda 2. And then lambda 2 gives you your phi squared over 2. Okay. The only thing is that because we have this 1/2 we're carrying with us the whole time, now this will become divided by 4 instead of divided by 2. But then otherwise we do the same thing as before. Okay, so nothing special. So the real thing is that we're so concerned about mu n, but actually the lazy random walk mu n is no big deal. Like, yeah, as was clearly pointed out, the spectral gap will always be just the second eigenvalue. Your averaging was 1/2, but it's okay. All right. Okay, so we do get this convergence for the lazy random walk relative to the conductance, which has this very nice interpretation in terms of these bottleneck cuts in the graph. Okay, good. Questions? All right. So I think then the rest of the class is actually trying to prove this thing called Cheeger's inequality. It's called Cheeger's inequality because Jeff Cheeger has a kind of related result for manifolds, kind of something about the size of a boundary on a manifold. And okay, so the first half is not as hard. It's a little tricky, but it's given as an exercise, kind of broken down into steps. The second half that we'll focus on is much harder though. Okay, so yeah, like homework. Yeah. So we'll focus on, and the second half is really the algorithm, where we're really going to figure out how to take an eigenvector that attains this and pull out a cut that's less than equal to this. Yeah. Okay. Good. All right. So that's the plan. We're doing okay. All right. Okay. So what are first just the high level ideas? Okay. So at some level, we're trying to connect the conductance to some eigenvalue, the square root of an eigen. Somewhere square root is also going to show up. You have a chance to figure out when and where. So okay. We know a lot about M, right? Because M's a symmetric theorem, symmetric matrix. It has some kind of diagonalization. We actually know that so here I'm listing the eigenvalues from smallest to biggest. Okay. And we know the smallest eigenvalue is 0. Okay. And we also know that V1 is going to be the kind of same eigenvector because it's just I minus R kind of thing. I think this should actually be of Q. Okay. Uh, so, but in any case, this was what we already know. So we actually know also what the first eigenvector is. Of course, at some level, the eigenvalue is 0. It just sends it to 0. But the point is that we know that V2 through Vn all live in the space orthogonal to this vector. Okay. So in particular, if I wanted to try to find V2, right? So lambda 2 is attained by V2. But we can kind of write it as this optimization problem where I'm minimizing this ratio over all vectors orthogonal to V1. Okay, so orthogonal to kind of the square root of the degree matrix. And that'll get you V2. Okay. This is important because that's something we can actually try to compute. Okay. I guess we won't necessarily do it in class, but you can compute eigenvectors. That's sort of important. We'll treat it like a black box, like LP solvers. Okay. And if we kind of undo that, y is equal to square root of dx thing, that's the same as saying I'm going to find x that minimizes xlx over x dx subject to kind of this weighted sum being equal to 0. All right. Okay, so that's a high level idea. So the nice thing is that we can directly solve this, but basically get this vector x, right? Which at some level is some continuous relaxation of conductance, right? But at this point, this ratio is exactly equal to lambda 2. And meanwhile, it's solving some continuous relaxation of conductance. So if we can take this and convert it into a cut of some low conductance, then that would be very good. Okay, so this would be greater than equal to some cut that's induced by x, or we get out of x. The question is, how can I convert the eigenvector to a cut? Just at a high level, any ideas? Like you may be able to guess the algorithm, but you have, yeah.
Probability distribution of what you take.
Oh, okay, maybe it's a probably so one thing I should point out, for example, x can have negative values. X will certainly have some negative values since this is a positive vector. So okay, can I interpret x as a distribution, just sample vertices? Well, it starts to get tricky because you have negative values. Can I square all the values and maybe do something proportional to the squares? Maybe, but once you square, you might lose some of the information, right? All right, any other ideas? Yeah.
Some like bound and just get the ones of greater value than that.
Pick some value and take everything above it. Yeah. Have we done that before? Yes. All right, so we showed this thing, right? Whenever we did this for Maxwell min cut, and you could just order them on a line and do a sweep cut. So that's at least a natural idea, right? Because you can see that at some level, right? When x is trying to minimize xlx, right? And L really captures cuts, right? So it wants to kind of put endpoints of the same edge close together because you take the difference squared. So you can think of x as kind of trying to line up all the vertices so that all these kind of sum of squares of all the edges along the line is small. Okay, so it seems to kind of try to correlate vertices along the line intuitively. So there's maybe some intuition uh, behind trying to do this, at least why it's a natural heuristic. And in fact, this was a heuristic before I think it was analyzed rigorously. Yeah.
But what's it sure like all values of theta will give you
Okay, so if I told you that the average on the midterm was 100%, what do you know about how everyone did? That everyone got 100. The same logic here. What? So we showed that the average cut gets the minimum cut, and you can't do better than minimum cut. So the average cut is doing perfectly. Okay, good. Okay, so what we're really going to focus on then is that the line embedding perspective of x is going to do some kind of line cut that satisfies this thing, and that kind of maps to our theorem. Okay, if you plug in lambda 2 here, that's what you'll get. So that's what we want to show. It's going to be a little heavy on the math side. I don't know if, well, relative to what we normally do. Okay. All right, good. So, okay. So, right. Okay, so what we're going to do is first prove a special case. Okay, I'm going to assume x is nice in two respects. I'm going to assume x is non-negative. That's in general not true. And I'm going to assume that the total number of vertices, if I look at all the vertices that have strictly positive value or non-zero value equivalently, since it's non-negative, and I look at their volume, it'll be at most half the volume of the graph. Okay, so any subset of these positive vertices will always be kind of a small set from the perspective of conductance. It'll define the denominator of that ratio. Okay, so that's going to be a convenient thing, but this is still where most of the work will happen. And then we'll figure out how to take a generic x and turn it into kind of this non-negative thing with small support. Okay. All right. Good. Okay. So, so let's do this. Yeah. All the vertices was non-zero value, which since it's non-negative also means that's strictly positive value. Okay, so maybe I could have written this as volume of the set of vertices where xv is greater than 0, which would have been the same as not equal to 0 because it's non-negative. Okay. So what does that look like? That means you have like some value z 0, and this goes off, some large number. So you have a bunch of vertices over here, and you have a bunch kind of stacked up here. Okay, Okay, and I'm saying that all of the volume of the strictly positive is at most half of the volume of the entire graph. Okay, in particular, all of these sets that look like this will be one of those kind of smaller halves when you look at the denominator. Okay, so these are all small sets in the strictly positive space. Okay, so that's a little bit convenient. In general, we could have vectors on the vertices on the other side too, but we'll figure that out later. Okay. Okay. Well, let's just do it. But I think line by line, you may be able to guess several of these. So, let's see what happens. Okay. Let me first set up some notation. So, all right. So I'm going to number the vertices in decreasing order. And let's say there's k positive vertices out of n possible. Okay. And then S1 will be the biggest vertex by itself. S2 will be the biggest two vertices. S3 will be the three biggest vertices. That will be kind of our sweeping sets. Okay. All right. So at some level, we're going to show that some of these sets must be good. Okay. But actually, we're not going to really focus on extracting this set. We're going to just prove the bound and be clear why there's an algorithm afterwards. All right. Now, I guess I'm going to start from here. All right. Phi x dx. And I'm not going to do anything special initially. I'm just going to, huh? Oh, it's down here. Okay. I'm just going to write it out. Okay. So we're just summing up over all the vertices, their degree times the square of their coordinate, right? Because that's just what it is. Okay. So nothing special. Now, okay. Why am I having so much? Okay. Now what I'm going to do is I'm going to rewrite this as a difference of volume. Why is that true? Okay. So this is going from the I minus 1 biggest to the I biggest, 9 biggest to the 10 biggest, the 10 biggest to the 11 biggest. The set induced by the 10 biggest values. Sorry? The volume is just a sum of degrees. Okay. Actually, my reasoning is not very good. Just like forget that. That's not true at all. Okay. Yeah. Uh, okay. All right. It's just the degree is a difference, right? You're just adding a vertex. You add a degree. Okay. Now the next line is going to rewrite it like this. So I think my reasoning's wrong again. I don't know. I was drunk. Okay. Hanging out with the Jonas Brothers too much. Okay, so I'm gonna put volume here. I'm gonna rewrite it like this. So what's going on here? Huh? That's what I wrote, but I'm not really, right? I'm really interchanging terms. Uh, okay, like what's the point of making these slides? I think you guys learn more from my mistakes than what I actually teach you. Okay, so interchanging terms will get you the second sum. Okay, good. All right, so at some level, okay, nothing too deep so far. We just wrote out a sum. We interchanged some terms. All right. Okay. Does anyone want to propose what we do next? No, there's no telescope. There's no telescoping anywhere, in fact. Maybe actually, I don't know. We'll find out. You just let me know when we finally get the telescope. That guy. Uh, survey says. Yeah, we do eventually need to get to XLX somewhere. Okay, so, all right. What do I know about the volume of each cut relative to the size of the cut? Well, how about this? Suppose I wanted to get rid of the phi. I want to get rid of phi. So this disappeared. And I'm going to somehow use this and replace it with something else. The weight of the cut. Okay, so here we're finally going to induce, this is where we actually use conductance, right? So this is a small set. It represents less than half the volume of the graph. So the weight of the cut is at least a phi times the volume. Or this divided by this is at least this. Okay, so the way the cut is always something big, conductance times the volume. Okay, so now we got something like that. Okay, and I'm just expanding out the terms. Okay, now what? All right, how about this? Okay, so suddenly things became much more compact. So before I'm summing up over all the level sets SI, I'm looking at their cut, and for every edge in the cut, I paid the difference between the ith vertex and the I plus 1's vertex. Okay. Now here, I'm going to the weight of the edge and just looking at the difference of the endpoints of the edge. So what happened? This is obviously nice because it starts to look more and more like our Laplacian. But how did I get there? Yeah. Yeah, so some level we switched to sum, but then how did I collapse this? Yeah, actually, I think so. We did it, guys. But maybe a picture would be easier. Because at some level, I have u is equal to some vi. So let's say v1, and then v is equal to, I don't know, v10 or something, right? And so that's their absolute difference, I guess, squared. But the weight of the edge appears for every consecutive pair in between it. I should in principle draw like 9 of these dashes or something, right? V2, V3, V4. Okay, so you're gonna get all of those in between segments, and then it's going to, alas, telescope. Okay, so so we're making some progress. Okay, now let me I can take that and write it out as I erased something by accident. As something like this, right? Okay. All right. What should I do next? This is an inequality we have not used before, but it's really exciting to use it. We're going to use the Cauchy-Schwarz inequality. We're going to use the Cauchy-Schwarz inequality. This is where the square root comes into play, which leads to this tyranny of the small set expansion hypothesis and all this messy theories, all because of the Cauchy-Schwarz inequality. Okay? It's whatever you want it to be. I get half the math wrong. Who cares if I pronounce it right? Okay. All right. So this is a sum, right? So Cauchy-Schwarz says the dot product is less than or equal to the two norms. Okay. So this is one of the norms. So you're taking a square root of WE on both sides and squaring it on both sides. Okay, so you're splitting the WE. So you recover WE's on both sides here. And then here's the absolute difference squared. Here's the absolute sum squared. Okay. All right. Are we making progress? Okay. Now what? Yeah, the one on the left is XLX. Okay. Now, what are we going to do about the one on the right? Okay, so if I can expand it out, right? XU squared. I mean, this is just expanding out that product. And I kind of want to. I'll tell you what. My goal is to eventually get to something that looks kind of like x dx over here. Okay. All right. So how can I do that? So x dx does look like these xu's and xv terms are good, right? So only problematic thing is this cross term. How can I bound the cross? Yeah. AMGM. What does that tell you? It tells you that XU, XV is less than or equal to XU plus XV over 2 squared or something. Sorry? So I don't think it's because of AMGM, but actually I want to get to here. Well, why is this true? That means I've implicitly the trivial inequality. So trivial that surely. So somewhere I use this, right? But what is this? This is not AMGM, I don't think. Okay, I just think of this as xu minus xv squared greater than or equal to 0. Oh, okay. Okay. We'll come back to that. Anyway, this is not a deep thing, right? Because it's just expressing xu minus xv squared is greater than or equal to 0. Okay. But the nice thing is you remove these cross terms, and now these xu squares, xv squares multiplied times the edge weights start looking like x dx, right? Because the sum of edge weights will recover the degree for each edge, for each vertex. Okay, so right, so this becomes 2x dx. Okay, so here, a particular u is going to appear in the sum in for all of its edges, and it's going to appear 2xu squared, right? And then the sum of edges will give you the degree. Okay, so great. So we've actually made a lot of progress, right? I started with this. I ended up down here. So you get something like this. Yeah. It's a little different style of proof. It's just kind of a hardcore kind of linear algebra proof. Use Cauchy-Schwarz in the middle, right? But if we start flipping things around and squaring both sides and things like this, you should get the conductance squared over 2. Okay. All right. And if you look back, you'll find that one of these cuts has to give you this low conductance thing. Okay. All right. Good. So that's the meat of the proof. Okay, we haven't lost yet. Okay. All right. So originally, I wanted to be able to take any vector that's orthogonal to D and extract out a low conductance cut. And what we just showed in sort of that long derivation is that if x is non-negative and to support, all the positive vertices have small total volume, then you can get a small cut. Okay. So now we just have to reduce one to the other. And we're going to do that with 2 claims. One, I'm not in on the joke, is that if you translate x, you only decrease this ratio. Okay, so you could always translate x, and it'll only help you. Okay, and the other is if I split x into its positive and negative component. Okay, so I just take the subvector of all the positive coordinates and the subvector of all the negative coordinates, but kind of make them positive. So in other words, x can be written as x plus minus x minus, where both of these vectors are non-negative, right? This is gobbling up all the negative coordinates, this is gobbling up all the positive coordinates. Then xlx will be always at least, the xlx for the positive coordinates plus the xlx for the negative coordinates. Okay, we can show that's not, each of these will be much easier than what we just did. And then meanwhile, x dx will be at most x plus dx plus and x minus dx minus. Okay. All right. So now my question is, how can we use the claims and our lemma in combination to prove what we ultimately want? We want to ultimately be able to take, well, we want to prove this. Well, yeah, it says, okay, so it says we want, and we want to show this inequality and also kind of get a cut, right? And so we can get this vector x that solves this problem, and we probably want to output a cut, with some value that's comparable to lambda 2. And the lemma kind of lets us do this if x was non-negative and all the positive coordinates cumulatively had kind of small volume. Yeah, so you'll want to split it up. Okay, so all right, so okay, so these are two claims. So okay, so step one of the algorithm is just to get your vector x solving that problem, right? Okay, so that's step one. All right, now what should you do? Yeah. Not necessarily, because that one is the minimum subject to the inner product of d and x being 0. So you'll break that rule when you translate by 1. Okay. Oop. Uh, anyone not pay? Okay. What do you do in step 2? What should you do next? What should you do? Just discuss. What should we do? What do we want to try to do? We want to split them up, okay. But if you split them up right away, what would happen? If you split into positive and negative right away? You might have this issue where, I don't know, x plus has way too much volume over its positive core. X minus has too much volume. Okay, so we have to fix that first. What does this mean? Okay, so we can shift it. So if we choose alpha to be like that breaking point to capture half, I could choose some value alpha. So if I look at everything strictly bigger, this should probably be minus. Everything strictly bigger than alpha, you'll get volume at most half. Everything strictly smaller than alpha, you get volume at most half. All right, so you figure out the point to split it. So on either side, you have strictly on either side, you have almost half the volume of the graph. Okay. Well, yeah, we haven't proven the claim. We'll do that. Okay. But now the next step is to split it. Right. So okay. So now, why is splitting good? They're both positive, so you can apply the lemma, but at some level you need to know that the ratios are good, right? So I want to show that at least one of these two have good ratio. Why? So you know something about that's right. Okay, so that's your first inequality. Okay, so whenever you have this like minimum of two fractions, it's always going to be less than equal to kind of if you sum the numerators and sum the denominators. I think that might have come up in Sparse's cut or in the notes. Okay. And then what do we know about this? Yeah, now we have that claim. And now x is the thing that attains lambda 2. Right? Okay. Now, if we apply the lemma to each of these, then we're going to get that the conductance of our cut, is at most the minimum of the two ratios. And that's at most lambda 2. So once we can do this translating and splitting up trick, then we can apply that lemma 1, which really did all the work. V is like the total sum, total volume of the whole graph.
Wait, so why is the x being greater than less than x being less than why is that?
Oh, so if the number isn't completely divisible by 2, you probably want to set alpha to be on a vertex. So you set alpha on the value of a vertex. You only have to look at the things that are strictly less and strictly bigger, and you end up removing the volume of that vertex you're hitting.
Oh, okay.
Yeah, just to break ties, and yeah, it's not an essential thing. Yeah. Oh, okay. All right, does that all make sense? So we just have to knock off these claims, and they're not so bad. All right. We could do this one first. Actually, I liked how it's written here. Okay, so this says that if I translate x, the ratio will only go down. Anyone see why? Okay, so we're going to verify directly, but I just want to briefly mention that when you translate,
It's the L one is like the difference squared, and like when you translate the difference, don't change.
yeah, okay, so yeah, so the numerator won't change. I only wanted to mention that at a high level, when you translate by 1, you're sort of mixing in that first eigenvector, the space from the first eigenvector, and that's only going to help. But it's easy enough to verify directly. So let's do that. All right, so this is equal. Why? It's because you're looking at all these terms that look like the sum of xu minus xv squared, right? If I add 5 to each one, the difference doesn't change. So numerator doesn't change. Once is in the kernel. Okay. Now for a denominator, I'm claiming that if you expand this out, there should be a cross term, right? There should be a 2x alpha 1s, but there's no cross term here. I've zeroed it out. So the question is why? Okay. So somewhere we need to use the condition that xd is 0. So if I look at x d1s, right, and that'll give me xd. That's 0. Okay. So it only increases the denominator to shift things, and the numerator doesn't change. So you can always shift. Okay, so all that's left is to prove this, and I will be brief in the interest of time. So we want to show that what XLX is bigger than the XLX for the x plus and x minus parts separately, and that XDX is at most XDX for the positive and negative parts separately. So maybe I'll just do the first one because the second one is more straightforward, and I'll leave it to you guys. So, okay, I want to show that XLX is at least x plus LX plus x minus LX minus. So to this end, I guess the first thing we can do is we can just write it out, right? So uh, since x is equal to x plus minus x minus x plus minus x minus, that things will just kind of distribute out like this. And I guess what we want to show is that this thing uh, but we want to show that the part that's underlined is negative so that the whole -2 times that comes out positive. And okay, so if I expand that out, I'm going to get something like this. I'm going over every single edge and looking at those kind of potentials at the endpoints. And we're looking at the difference of the positive part times the difference of the negative part. And so this, I think, if we can show that this individual product is positive, then we're in good shape. Indeed, or rather negative, then we're in good shape. And so then here's the claim we need. It says for any real numbers, here I'm letting a plus be the positive part of a real number and a minus be the negative part. A plus minus b plus times a minus minus b minus is less than or equal to 0. Okay, so how do we prove this? Well, it's just looking at it slowly. If we just assume that a is greater than or equal to b, then the first part is always positive, and the second part is always negative. So the whole thing comes out less than or equal to 0. This thing comes out less than or equal to 0. This comes out less than or equal to 0. That is greater than or equal to 0. And so we have our inequality. Okay, right. So yeah, so I'm going to skip this. I'll leave this as one of those amazing exercises. But it's not too bad. And yeah, so let me just wrap up then. So what does the whole algorithm do? We get the second eigenvector of the normalized Laplacian. That's also minimizing this sort of expression. We shift it by alpha so that the strictly positive and strictly negative part, again, I think negative, the strictly positive and strictly negative parts each have volume less than half the graph. And now we know that either the plus or the minus is going to attain the ratio we want, and we apply, the non-trivial lemma to both, and we get some cut with low conductance relative to lambda 2. Right? And so that sums up Cheeger's inequality. Most of our work was here. This first inequality is going to be a homework problem. And that's it. So next time we'll do something exciting. We're going to show how to get deterministic connectivity in logarithmic space. Okay, anything left? No. All right. Okay, thank you.